I'm very pleased today to introduce Dr. Wilke. So Claus Wilke is the Jane and Roland Blumberg Centennial Professor in Molecular Evolution at the University of Texas at Austin. He holds a PhD in theoretical physics, and he received his postdoctoral training in biological physics at Caltech. He has published extensively in computational biology, molecular evolution, protein biochemistry, and virology. And he has also authored several R packages for data visualization, including cowplot, ggridges, and ggtext. And he is a regular contributor to the ggplot2 package. And he has published the book, Fundamentals of Data Visualization. So I'm really excited to have Claus speak to us today. I actually use his software all the time to make beautiful plots. So we're really pleased to have you. Thank you for coming.
Yeah, thanks a lot for the invitation. Should I share my screen? Should I get going? Oh, I guess when I speak, you can't speak, right? Okay, very good. Okay, can you see this? You should see a web browser with slides in the middle. Does it look correct? Okay, very good. So let's just quickly set some ground rules. So you're welcome to ask questions as I go along. Probably the best way to do it is to just put questions into the chat. And then there are a couple of times throughout the presentation where there would be a logical breakpoint, and if I remember, I will ask if there are any questions. As I present, I can't really see the chat, right? So, but I think that's the best way to arrange it, to like collect the questions in the chat for one topic, and then as the topic comes to close, then we can go over the questions. Okay, so let's start, and let's start with putting things into focus. Why data visualization? So I'm, I guess, a biologist, but mostly now I think of myself more as a data scientist. Now, many of you in the room may not think of yourself as a data scientist. You may think of yourself as a biologist or a physicist or chemist or whatever it is that you're doing. Maybe you're doing computer science, maybe you're doing social sciences. But you probably in some way or another touch on data science. And so let's start a moment with like, what is data science? Data science in my mind is the intersection of programming, statistics, and communication. And so everybody that does a reasonable amount of data analysis in some sense does data science, right? You maybe you can get away without programming, but you rarely can get away without statistics. And you certainly cannot get away without communication, right? And so data science lives right at the intersection of those three. And then a major component of that is the visualization, because remember, we're in the communication sphere, right? We're very much in the region of activities, that is, we need to communicate whatever we've done to the outside world, but we need to do so in an informed and factually based way. And so that's where programming and statistics come in. Now, I'm not really going to talk about programming or statistics today. I'm only talking about communication. So this is only to set the stage. So now, why me? You've already heard I wrote this book, Fundamentals of Data Visualization, which, by the way, is freely available online at this link. It's an early draft in the sense that, like, we did some proofreading and some minor editing after this draft was put together, but basically you get the entire material there, and you should in no way feel uncomfortable about reading the free book rather than purchasing the book. So it was always the intent from day one that the book would be 100% free. And so I use the free version in all of the classes that I teach. That's what I tell my own students they should read. So go and read the free version. And then if you really want a physical copy, you're of course welcome to purchase one, but I do not have that expectation. So how did I get there? That was also already addressed a little bit, but maybe a little bit more background would be helpful. So I'm a computational biologist. I'm an active scientist. I have a group of graduate students and postdocs that are working with me. And so an important component of that activity is writing scientific papers and then preparing figures for those scientific papers. And what I noticed was I was telling my students and postdocs the same things over and over. I was saying things like, well, make the fonts bigger, or remove this background grid that's a bit distracting, like use these colors, don't use these colors. And so after a while of saying the same things over and over, I thought, well, maybe I can automate this. So we were using at the time already ggplot in my lab. And so I thought, well, if I write a package that sort of just sets everything up exactly the way I want it to be set up, then maybe my students will just make the figures that I want. And so this is really the origin of the cowplot package. Like the original idea was just, it doesn't do that anymore, but at the time it would change the default theme of ggplot and just sort of try to create an environment in which figures would pop out more in the way that I wanted them. So all my students and postdocs started using cowplot and would still prepare figures that I really wasn't happy with. Like they would somehow manage to circumvent all the settings that cowplot automatically set up for them and still like make the labels too small and so on. And so then I realized that like judgment cannot be automated in an algorithm. You actually have to tell people why things should be done a certain way. And so this led me to ultimately writing this book, which is entirely conceptual, right? I do essentially all my data visualization with R, but the book is not an R book. There isn't a single line of code in the book. The book is entirely about concepts. Why do we do things this way and not that way? What are good choices or bad choices that you can make when you prepare data visualizations and so on. Okay, so with that introduction, today I want to talk about 3 key principles of effective visual communication. And the first one is going to be tell a story. That's actually bigger than just visual communication. That's any communication. So that will also apply to writing papers and any other form, giving presentations in a talk. All of these things will be covered, basically. Then prepare figures that make a point. And the last one is going to be make your figures accessible. So all these 3 are very, very big topics. I don't really have time to go into the specifics of how do you make a box plot or anything like that. At UT Austin, I'm teaching a semester-long course on this topic, right? Like you can talk for a lot longer than an hour. So I just focus on a few key principles that I want everybody to know. Like if you know something, you should know these 3. So, okay, tell a story. So what is a story? Here's the definition. A story is a collection of observations, facts, or events presented in a specific order such that they create an emotional reaction. And the emotional reaction is highlighted in red because that's what matters. You can present a collection of observations, facts, or events that don't create an emotional reaction. And that's fine, like a list of participants here at this event today is certainly a collection of facts, right? Observations of facts, but it's not really going to create an emotional reaction unless like there's a participant maybe that you particularly like or particularly dislike, then that would create an emotional reaction, but just the list of participants is not going to create an emotional reaction, right? But the emotional reaction is what matters, is what makes your audience care about what you're presenting, what you're talking about. Now, in the context of scientific reports, like science in general, people often are concerned when they hear the word story because they think, oh, somebody is just making things up or somebody is like overselling. None of that is in the definition, right? The definition doesn't say made up things. The definition doesn't say invented or like oversold things. The definition just says observations, facts, or events, which you're dealing with all the time when you're doing science. And then you have to create an emotional reaction. Okay, how do we do that? So there's this concept of the story arc, which essentially just means that there are specific structures that we can follow to ensure that we have at least some amount of emotional reaction. And the most common one, certainly in the context of writing scientific papers or giving presentations, is the following. You have an opening where you just tell your audience broadly what you're working on, what the topic is. And then you present a challenge. And then you have an action that follows that challenge, that addresses the challenge. And then at the end, you have a resolution. And the two things that really matter are the challenge and the resolution. And in my experience, and again, so there's many postdocs here, probably graduate students, other scientists. All of you have been in, say, PhD committees or presentations by fledgling scientists. What you often see is presentations that spend all their time on the opening and the action, right? The typical graduate student presentation will first, like for 20 minutes, if somebody told the graduate student you have to present background, then they'll for 20 minutes will talk about just general background. And then for the rest of the talk, they'll tell you what they did. They never actually tell you what the challenge is. I shouldn't say never, often they don't tell you what the challenge is, and they don't provide a real resolution for the challenge. But those two parts, those are the things that matter. You can skip the opening, but you cannot skip the challenge. You can keep the action very short, like what you exactly did can be very brief, but there needs to be, in the end, a resolution to the challenge. And that's then what's going to create the emotional reaction. And there's different ways that it can go, right? So the purpose of the challenge is to draw the audience in, to get them engaged. And then they may think about what they think the resolution is going to be. And so if you then resolve it exactly how they thought you would, then the emotional reaction is one of satisfaction or maybe pride or just general joy, like the audience, they got it right, they figured out what you were going to do and they predicted it. So you have like made them a part of the discovery process, right? The alternative is if your audience is completely wrong about how the challenge is going to be resolved, then usually if the resolution is real, like if it's not a disappointing ending, but if it's a satisfactory ending, then the emotional reaction will be one of surprise. And that's probably even better of a reaction to achieve. If you can achieve that, you should always shoot for that. Okay, so let's take this structure and map it onto my story. So there's a reason why I started talking about myself at the beginning, because I was actually trying to set up the story in this way. So the opening was, in my lab, we need to make many data visualizations. And then the challenge was, I end up telling my students the same things over and over. So that the challenge really is the students don't really know how to make data visualizations in a way that I want them to. Then the action is I go and write a book about data visualization. And then the resolution is the book is written. And now I teach the material, so I still keep saying the same things over and over. So, and I hope you can see how what I said at the beginning of the talk sort of followed this outline, right? But that's not the only way you can tell a story. And it's actually important to be aware that there's different structures, because that allows you to choose the right structure in the right context. So, for example, the following structure can work also very well. And once I've described it, you'll see that you know it. So I can start with the action, and then I go to the background, and then I go to the development, and then I go to the climax, which is basically like the resolution. And that's, and then it ends. And that's the standard script for an action movie, right? If you think about any action movie, like, I don't know, Mission Impossible or James Bond or whatever, they always start with the action, right? The very first scene is like somebody jumps out of an airplane and like onto a boat, and then there's a speedboat under a bridge, and like somebody shoots at him, and you have no idea what's going on, but there's a lot of action. And that goes on for a little bit. It's actually important that the action is not too long, because if there's tons of action without any reason for it, you will get bored. But if there's a little bit, it may be just enough to draw you in. And then it goes to the background, right? And suddenly it like says like 5 years earlier, and you have like people sitting around in a dinner table talking about something, right? And so that then slowly goes to what is actually going on in the story and so on. So again, it's typically used in action movies, not necessarily in scientific reports, but we can try it out, right? And we can see how it works. So for example, I could have told my story in this way. In May 2017, I embarked on a major project, write a book on data visualization. I do this because we need to make many data visualizations in my lab, and I end up telling my students the same things over and over. Writing the book takes me almost 2 years. Along the way, I add many features to ggplot2 and become a member of the ggplot2 team. The book is released in 2019, and now I'm data visualization teacher. Same story, same facts, same events, different order of presentation. And now the last one is actually very, very useful in many contexts. It's simply lead development. So that's what you commonly use in newspaper articles. So the lead essentially gives away all of the story at once at the beginning, and then the development fills things in. And so my story on that format would be something like, because I see the need for more education data visualization, I've written an entire book about the topic. So there we go. I've given everything away, right? Nothing like left to be resolved later. And now I can give you the development, which gives some background and so on. I previously written an R package to improve figure design, but it wasn't sufficient. Good judgment cannot be automated. So write a book. The book is entirely about concepts, not about coding, and is meant as a resource for anybody doing data visualizations, regardless of their preferred visualization software. Do you have another sentence there? I don't. Okay. Let me actually go back 2 slides for a second. So here I say this is commonly used in newspaper articles, but it's also actually the preferred format that I recommend everybody to use in personal statements or like fellowship applications or anything of that sort. Actually, research statements, if you're applying for a job and you need your, like, there's always like this, oh, please submit a research statement and a teaching statement and so on. I strongly encourage everybody to use this format in those kinds of statements. Like the first paragraph, if you give me your research statement, I should be able to just read the first paragraph and know everything you're doing, basically. At a very high level, of course. I mean, you can't put a lot of detail into your first paragraph, but the first paragraph should tell me the entire story, right? Like if I try now, I have not prepared for this, so it could go terribly wrong. But if I try to do this for myself, I would have to say something like, I'm a computational biologist and I use computational methods to predict mutations in proteins. And our primary goal is to be able to engineer proteins so they can solve meaningful problems. For example, we are developing peptides that can be used as antimicrobial agents. And we're also working with protein engineers to find mutations that we can make to introduce novel function or enhanced function in enzymes, something like that, right? So that was just a few sentences, and it hopefully gives you a complete overview of the kind of stuff that I'm doing without really going into any specific detail. And I will go like a little bit off script now and also say, so as department chair, I have hired a lot of faculty members, and I always at some point have to write a letter to the dean where I have to say, who is this person? Why did we hire them? What are they doing? And so I go to the research statement, and rarely does the research statement actually give me the material that I need for the dean, because I don't need 5 pages of detailed experimental plans, right? I need this 1 paragraph that tells me, what are you doing? How are you, sorry, not how, why are you doing it? and how are you making a difference, right? So just something to keep in mind, like the thing that frustrates me the most, so think about if you can address it in your own statements, is when people say they're investigating something, but they're not really saying what they have found, right? It's very different if you say, well, I have studied whether we can make new antimicrobial peptides. That's a project I'm working on. Versus when you say, I have discovered 3 peptides that have antimicrobial activity, right? Completely different message. So think about like the question that I rarely see answered, and I want it answered in the very first paragraph, not somewhere in page 3, is like, what have you discovered? What have you found? How has it answered your question, right? The resolution to the challenge needs to be there. Many people have a challenge, but then don't actually provide a resolution to it. And I know you feel like you're early in your career, there's still 20 years of work ahead of you. That's true, but you have published things, right? You have done some research, you have made discoveries. So there has to be something that you have found. There has to be a resolution to a challenge. So with that, that is the end of the first part. So this is maybe a good time to just take a minute to see if there are questions, or if anybody wants to raise their hand and ask a question live. Okay, then I'll just keep going because I was already 30 minutes. And you're welcome to ask after the second component. So the next topic is prepare figures that make a point. So let's go back for a second and say, okay, I just talked to you about telling a story. So how do we use figures to tell a story? And the most important component here is that every figure needs a clear purpose within the story arc, right? So there's actually 2 statements in this bullet point. The first is you should actually know what your story arc is, right? You should know what your challenge is, what your action is, what your resolution is, and so on. And then for every figure that you make, you should be able to assign it to different components in this story arc, right? This figure is an introductory figure. It's an opening figure. It just sets the stage. This figure creates the challenge, right? How does a figure create a challenge? Well, maybe there's like some unique aspect to the data that can be seen in this figure that immediately creates a question, right? Like, why are the red points over here and the green points over here? We would have expected them to be next to each other or something like that, whatever it may be. Action, like if you have a figure that shows like your experimental protocol, or you have some sort of diagram that lays out what exactly you're doing, that would probably be a figure that belongs into the action part, like what it is that you're doing, which is fine, but then it probably shouldn't be the first figure in your paper. And then ideally you have a figure that somehow provides a resolution. That can sometimes be the most difficult thing, but I will show you now in an example how one could do that. And then the other component is that a complete arc will usually require at least 2 figures. And that's because if you try to put the challenge and the resolution into one figure, then you don't have this temporal separation of first challenge and then resolution. And then the consequence is that there's just less of emotional reaction because there's less tension that you've created, right? It can still work. I mean, again, there's the lead development storyline where you give everything away in the first sentence. If you think that your audience has a very short attention span, that's maybe what you have to do. But if you can create a bit more of a separation, if you can build up some tension and then resolve it, that's usually better. Okay, so let's do this. And the example that I'm going to use is preprints in biology. So I don't know how many of you are biologists. I don't know how many of you are using preprints. So I'll just give you like the full story that I normally tell to people that maybe aren't even in science. So preprints are articles that have not yet been published, right? That have not been successfully reviewed and formally accepted for publication. So people just post their works online before the review process, and that has a long tradition in physics. Like I did my PhD in '99, and like in physics, and we're already reading preprints and posting preprints and so on. And the traditional physics preprint server is called, yeah, I don't know how to pronounce it. I think archive, but it's written arxiv. And so around 2007 or so, they introduced a quantitative biology section, QBio, and biologists slowly started posting preprints there. So you see the number of preprints per month posted as a function of time. And this is a log scale. So a straight line actually is an exponential increase. So the numbers were low, but the growth was exponential. More and more biologists, quantitative biologists, were posting their preprints. And then in 2014, there's a complete change in pattern, right? What happened in 2014 to curtail the growth? That's the challenge, right? And now I encourage all of you to spend a moment and to think about, like, what is your explanation for this pattern? Why do you think that there was this dramatic change, right? Give you 30 more seconds to think about it. Okay, and so here's the resolution. The biologists got their own preprint server, right? bioRxiv, which was sort of modeled after arXiv, but was specifically for biologists and run by biologists. It opened in 2014. I think it was, I don't remember the month, but sorry, it was in 2014, and it had like enormous success. You see, you have again exponential growth, but much, much higher exponential growth. It's actually interesting that like the quantitative biology preprints didn't like fall off a cliff, but like kept going. So I guess there was like some hardcore group of people that like were happy with the physics preprint server and kept using it, but most of the new like recruitment of new people that were posting preprints, they went straight to bioRxiv, and like growth was enormous. Okay, so this was an example of telling a story in, this was really 3 steps, right? So this was the introduction, the opening, and then this was the challenge, drawing your attention specifically to this change in trend, and then this was the resolution. And this sort of way of presenting, in my opinion, is particularly important when you're giving a talk, right? If you wanted to like post this as a tweet on Twitter, you'd probably have to just make one figure and like write like 1 or 2 sentences that capture the entire story, and you might get a lot of engagement like that on Twitter. But if you're telling the story in a talk, always think about building it up in stages, right? Show one thing first, like hold something back, give the audience enough time to figure out what is actually shown. Like I took the time to tell you what is on, I think I said what is on the x-axis. Normally I always do that, right? We have time on the x-axis, we have preprints per month on the y-axis. Really take the time when you're giving a presentation to say these things. And if your immediate response is, well, I have so many figures, I don't have the time, then you already have the answer. Yeah, then that just means you have too many figures, right? You have to have the time to tell your audience what is on the x-axis, what is on the y-axis, what is each particular line that you're showing. Because if you're not taking that time, your audience will simply not be able to process what you're showing at all. Okay, so, and this is a great segue to the next topic, which is don't overload your figures with irrelevant detail. It's, again, you need to give your audience time to process what is shown. So this is a figure about airline delays. It's marked as bad because I don't think this figure really serves its purpose, unless the purpose is to confuse your audience or to create an opportunity to spend 10 minutes in the talk to just waste time on explaining a figure that's not really useful. But I will now try to only lose 2 minutes on this, but I will walk you through it. So we have on the x-axis the distance flown in miles. So this is flight delays by airline, connection, and distance flown. We have the distance flown on the x-axis. We have the mean arrival delay in minutes on the y-axis. So 0 means no delay. So dots above 0, those are delayed flights. Dots below 0, those are actually flights that arrive early. A surprising number of flights arrive early. The truth is they arrive early because the airlines just budget more time, right? If the actual flight is an hour, they on the schedule write an hour and 20 minutes, and then they can have 10 minutes delay and still arrive 10 minutes early. That's the secret of airline flight scheduling. But in any case, each dot is a destination, right? So they're all out of New York City, and then maybe you have like Los Angeles somewhere here. So I don't know how far Los Angeles is from New York, but it's not right nearby. So it might be one of those dots. And then the coloring is the airline, and the size is the number of flights, right? So this is a destination where there's only a few flights from New York City to this destination, and this is a destination where there's more flights to this particular destination. And then I have trend lines for like American is blue, Delta is purple, and then other is sort of this orange. And you see, after staring at this for enough time, so Delta, the line is just systematically maybe 5 to 7 minutes like lower. So Delta has fewer delays, but it follows the pattern of other. And then American for short flights has even fewer delays, but for long flights is just as delayed as everybody else. So that's roughly what this figure shows. And it shows that, and if you spend enough time with it, this might be a useful figure. But if you're just quickly wanting to make a point, this figure is just not serving its purpose at all, right? Like if your point is just American and Delta have like the least delays, then just saying that in a very simple bar plot, for example, where we have the airlines here sorted by their mean delay in minutes, American and Delta have the shortest delays. That's a much more, it goes right to the point, and it gives your audience much greater ability to actually process what you're trying to say. Okay, and then the last component here is you should try to make your figures memorable. And what I mean by that in particular is like, so I'm a great fan of bar plots. I just showed you a bar plot and thought this was a great plot. But now I'm showing you another bar plot that looks just the same, but it's on a completely different topic, right? So this is now the number of dogs, cats, fish, and birds in households in the US. So in millions. Right, 43 million households have dogs, 36 million households have cats, 7.7 million have fish, and 3.7 have birds. And I made this bar red for no good reason other than that now this figure looks very similar to the airlines figure, but is completely different and completely unrelated, right? And so there's the risk that if you make your figures all look the same, that yes, individually they make a point, but in aggregate, it all blurs together, right? Like if I showed you 10 bar plots like this on 10 different figures, 10 different topics, and then an hour after the talk, I asked you, well, what did you see? You'd say, well, I saw a lot of bars. Sorry, I don't really remember. Like somewhere about flights and somewhere about pets, but I don't remember which one was which because it's all the same, right? And so sometimes doing something that makes a figure unique, even if it's a little cheesy, can actually help. Right? So now I'm showing you the same plot, but actually with animals, right? Dogs, cats, fish, and birds. And there's two things that this does. One is, like, you can see this very quickly and look away, and you will still remember there's the dogs on top, and then the cats, and then the fish, and then the birds, because your brain immediately processes this and will be able to retain this spatial organization, right? And the other is, there's a good chance, like, if like 6 months from today, you're asked to remember one thing about this presentation, that it's going to be this figure, right? Because it's so different from everything else, and it's just so like unique and maybe silly on some level that it'll stick in your mind. And so just like remember that sometimes it's good to do something like that. So there's like this long history of a person who will not be named to introduce the idea of chart junk. And like at the time, there was certainly like, you can certainly overdo it and you can produce atrocious like visualizations and charts, and it's good to like clean them up and not overload them with unnecessary detail and so on. But at the same time, research now has clearly shown that these kinds of things, like using pictograms, for example, like we often see it in newspapers, right? Like you see, I don't know, like the number of soldiers died in a war, and it's shown like as little pictograms of people or things like that. Research shows actually that really helps your audience to memorize, to remember basically what you talked about. And in the end, I mean, if nobody remembers what you did, then the whole, like, there's no point, right? Like the point of giving a talk is that afterwards people still know about it and maybe talk about it, right? Like if there's a section of like, you present like as a series of 10 talks at a conference, and then there's a coffee break, you want people to talk about your presentation, right? If they still remember what you talked about and then talk about it, you achieved your goal. And so this is one way that you can do that. Okay, so that was part 2. And so do we have any questions or comments at this point?
I have a question,
Yes.
and if anybody else has one while I'm talking, feel free to like prepare your question as well. So you've been talking about having like a single point in each plot.
Yeah.
And that makes a lot of sense in the context of a spoken presentation. How do you tackle like a paper, a journal article? Do you still try and keep the plots very simple with one point, or do you do multiple things in one figure?
So I think like subpanels are a good idea. I'm generally in favor of subpanels. But I would say I have seen so many like figures in papers that just totally overload the reader. And I mean, I'm sure you all know it. Like we experience it in our journal club all the time. Like and it's like the more high profile the paper, the more of a problem it is. Like there's like a figure with 10 panels, and then each panel shows like a million different data points, and like top of that, possibly highly derived data. So what I mean by that is like, instead of showing the raw data, you first calculate a correlation, and you calculate a correlation for a million different conditions. And then you take those correlations and you correlate them with something else. And then you have this like really colorful figure at the end, and nobody understands what's happening. So I'm somewhat critical of that, I would say. I'm also like, you need to show your evidence, but like sometimes having the evidence in the supplementary materials is fine, right? Like if somebody cannot in a short number of minutes read the figure and actually figure out what it's showing, then I would argue you have not actually managed to communicate effectively. And I'm sure some people disagree, and that's fine. Like there's different purposes at different points in a communication, but just think about that, right? And think about yourself. How often have you seen highly complex figures that you did not understand? Just be honest about that, right? And so if that happens to you, then it probably also happens to people that see your figures if you make those kinds of figures. Okay, there's a hand. Can the attendees talk, or are there like microphones off?
Go ahead, Tara, you're unmuted, I think.
So Tara shows as muted in my.
I can't, I've given them permission to speak, but I can't seem to actually, well, obviously I can't control their microphone, so maybe we'll come back to that question in a little bit.
Yeah,
or
they
Tara, if
may
you'd like
have to
put it
unmute
in
themselves.
the Q&A,
actually.
if you're having trouble with your microphone.
Oh, now I see the chat is disabled. Okay, anyway, I'll keep going because the last topic is actually kind of important. So the last one is make your figures accessible, and that there's many different elements to that. I'll touch on some of the most important ones. Almost certainly the most important overall is colors, right? Design for color vision deficiency. 5 to 8% of men are colorblind, and I'm writing men because like women, like just genetically are less likely to be colorblind because the color vision receptors are encoded on the X chromosome. So that's why there's this sex-linked property. And so that means like if you have an audience of 100 people, you can be certain that somebody in the audience has color vision deficiency. So this is what that means if you haven't really ever thought about it. So here on the left where it says original, I'm showing you like a red-green gradient like we would use often if we, like, for example, in biology, gene expression analysis, like some genes are upregulated, some genes are downregulated. So you use green for the upregulation and red for the downregulation. That seems like a very natural contrast for anybody who has functioning color vision. And then for people who have some sort of red-green color vision deficiency, and there's two, like deuteranomaly and protonomaly, it's basically, can you not see red or can you not see green? But the outcome is the same. So this is like the original color gradient simulated under color vision deficiency, and you see in the deuteranomaly, like both ends look the same, and in the protonomaly there's a bit of a difference, but basically they also look the same. And then there's a third type of color vision deficiency that is a blue-green deficiency. So they are fine with red-green contrast. They have problem with blue-green contrast. And I will also say, if the top left looks to you like the top right or the bottom left, then you have color vision deficiency. So this is the green-blue color vision deficiency, where then like the people that have red-green deficiency, they see this contrast. The colors may look different to them than to somebody with full color vision, but they can see that the left and the right colors are different. But somebody who has trigonometry, for them, the two ends look the same, and so they cannot distinguish blue and green. So there's many ways around it. One of the easiest ways around it is actually to use colors that sort of are clever mixes of the different colors. So if we take this contrast here, for example, if you have regular color vision, you might see this as a red-green contrast, but this is actually on the left, it's not red. It's more like a magenta. There's like some blue mixed in, and this is not a simple green. There's some yellow mixed in. And so then under the various color vision deficiencies, like even though the colors here look completely different, like to me, it's a red-green contrast, and then to somebody with deuteranomaly, it's a blue-yellow contrast, but it doesn't matter. It's a clear contrast, so that works. And then the trigonometry, for them, it actually turns into a regular red-green contrast because they don't really see the blue that makes here the original that creates the magenta. So that's a simple way to do it. And then there's a color palette that I always recommend, which is called the Okabe-Ito palette because it was invented by two people called Okabe and Ito. And so that's a pretty good palette that you can use if you need discrete colors. So this does not give you a gradient. This just gives you discrete colors. And you just have the hex codes here that you can like use in basically any, like if you design your figures manually in Illustrator or you use any sort of visualization software, it's generally possible to just enter the hex code for the color and get those colors. But one thing that is very important is we have to be aware that the extent to which somebody can or cannot see colors actually depends on the size of the element. So I'm showing you here in the top left original, like here we have like large colored areas, and then we have thick lines, and then we have thin lines, and then we have dots. And you may notice that it's much easier to distinguish the large colored areas than it is to distinguish, say, the thin lines or the dots. So depending on the quality of your screen and whether you're like in the room and it's projected, or you look at it on your laptop, you may already not be able to, like, on my screen, I have a very nice, good color screen, so I can see here these 4 colors, but even here for me, like the blue and the green here, the tiny dots are very difficult to distinguish. And now if somebody has color vision deficiency, fundamentally, that just means they're perceiving less color overall. Like, it's not that they see everything in grayscale, but things are not as colorful and everything is a little dimmer. And so then here you see they may be able to distinguish these large colored areas, but they may not be able to distinguish the tiny dots or the tiny lines. And so, like, on my screen, for me, with pretty good color vision, these 2 dots here at the bottom right are completely indistinguishable. I just can't see the difference in those 2 colors because they're so tiny and so similar that they just don't look different. Versus these look totally different to me. So this is something that you need to be aware of, that, like, in general, even for people who don't have color vision deficiency, very thin lines or tiny dots, it's really difficult to see the colors. Like, ideally, if you use colors to separate categories, you have somewhat largish areas that you're coloring, or if it's lines or dots, lines need to be thick, the dots need to be large so that the colors actually can be seen. And then the other thing is, like, even if the colors can be seen and even if the colors are fine for somebody with color vision deficiency, it may still not work. So here I'm showing you the traditional iris data set where we have like these different iris flowers, setosa, virginica, versicolor. I'm showing you the sepal length on one axis and the sepal width of the other. And we have the setosa here, the virginica here, and the versicolor here. And the blue and the green, even though they're distinct, to me, they sort of run into each other, and it's not that clear. I mean, yeah, if you pay attention, you can see it, but it's not immediately obvious which points are virginica and which points are versicolor. And so in this case, like, just changing which color is used for which species helps. So the orange and the green is much more distinct from each other. And now I've moved the blue to the top. And then the other thing that I've done is, on top of that, I'm also using different shapes now, circles, diamonds, and rectangles or squares. And now the virginica and the versicolor are really distinctly separate, right? Versus here, they run into each other. And it's a very subtle change, right? And so you have to pay attention to these things, and you may also have to run color vision deficiency simulations. So this is the original, like the first version, where the blue and the green run into each other. And if you run the color vision deficiency simulation, you see, like, for the trigonometry, for example, it basically is completely indistinguishable. Also, if you just print it in grayscale, it's completely indistinguishable, right? And even like these other like color vision deficiencies, it's not easy to see. But the revised version, actually, it still works even in grayscale, because you don't just have the color coding, you also have the shape coding, right? And the color really helps for people who see the color, but for people who don't see the color, they can then use the shape as a secondary cue to understand which points are which. And then one last thing is legend order. So here we have like a stock price example. So we have the stock price normalized to 100 at some point in time, over time, and 4 big tech companies. And you see that the legend order is alphabetic: Alphabet, Apple, Facebook, Microsoft. But the visual order is different, right? Facebook is on top and Apple is on bottom here. And so software never gets this right, because software normally cannot, like, the visual order is just how we perceive it, right? Because over here, Facebook is not the top, but it's only a small portion of the overall graph. So we perceive this as the visual order. And so then we would want the legend in the same order. So it makes it easier to read, but it also, if now you printed this in grayscale or so, you could still match it up. And ideally, you would actually not even use a legend at all and just directly label. That's the even better version. requires a little bit of extra work. So you may or may not have the time, energy, skill to do that. I mean, this is fine. This is better. This is not good. And I see this all the time. And so that's it. So the 3 key principles are: tell a story, prepare figures that make a point, and make your figures accessible. And with that, I have some further reading at the end, both from my book and from other people's books and papers. And I think the slides are just a website online, so I think you have been provided with the link. If not, we can certainly put this in the chat or send it out. And we have just a few minutes for questions. So, Harry, do you want to moderate the questions?
Yeah, so we have a question in the chat, and if everybody else would like to think about their questions, and I can ask again after that. And just on the topic of slides, if I haven't already sent out the slides, I will do it again to everybody who registered. So Corinne asks, thank you so much for your great talk, Professor Wilke. I really appreciate your work. Could you please speak on jobs or career paths other than academic science that have a particular focus on data visualization? I'm excited about using visual language to make complexity accessible, and I'm wondering what kinds of careers would allow me to do that.
Yeah, so so most of my trainees now actually go into industry. I almost never can convince them to stay in academia, because if you have meaningful skills in data science, there's actually so many opportunities and they pay so well that people just ask themselves, like, why should I take a postdoc and work for half the money, and that would be considered a well-paid postdoc. So so that's assuming that somebody has substantial skills in data science, but then actually they're almost always disappointed with what they actually do, because they've been trained to learn all these sophisticated skills of machine learning and so on, and then they go into industry and they realize 90% of the job is just data cleaning and counting, and then making like pie charts or bar charts or things like that. So I would say, like, from what I've seen, and I've talked to a lot of people in various positions in industry, like there's a lot of data visualization internally in industry. It's not necessarily good data visualization, but I mean, like any sort of business analytics, right? Like you need to figure out like how much money are you making, like where are your customers, what are they doing, what are they buying? Like in the end, all of that ends in some data visualization in a PowerPoint that like somebody gives to other people in their business unit or to management. So I don't know if that's the kind of job that you'd be interested in, but like those kinds of jobs are everywhere, basically, right? And they're almost like better suited to people whose maybe technical skills are not as high. Like if your own assessment of yourself is, well, I'm not like a superstar programmer, I'm not like a math genius, I'm just like somebody who like generally is smart and has some experience analyzing data and making figures, like you're probably almost better suited for the majority of industry positions. They may not know that themselves. Like you might have a problem getting into the door, but if you manage to get in, then you may be better suited, because like the people that are like so focused on very sophisticated analyses, they're like consistently frustrated that then in the end they can't actually do them. I don't know if that helped, but that's just my experience. So there's a comment about the animals. What's the best strategy to follow to make the visuals stand out yet not look tacky? I mean, have taste, right? Like, for example, often like very like simplified pictograms may be better. Like my images were photographic images, and I like somewhat on purpose like really pushed the envelope a bit there. But if you ask me like, what is my ideal image like that, it would be like more iconographic images, and ideally they would be like very well drawn. They also need to fit together, right? Like if you have like, for example, you have like 4 different animals, but the icons are very different. Like maybe one is grayscale and one is colored and one is very little, is very stylistic, and the other has a lot of detail. Then they don't fit together, right? That's like when we say tacky, it's usually just like things just don't have high quality, right? Like you want to make it unique and memorable, but at the same time give it some sort of it has to have the aspect of its quality work. I think that's the most important part. So yeah, resources. Yeah, I mean the slides for this presentation are all online, and then my book is also online, and then my book also has some additional pointers to go for. Like in particular, I would say if you're like interested in more broadly like storytelling, this book by Schimmel is really fantastic, and I think everybody should read that book. Now, you could argue I've basically told you what is in the book, because it's all like the entire book is essentially about like storylines and how do you map the things you want to say onto structures, story structures that work and so on. But still, like I learned a lot from this book. I highly recommend it. Okay, what's the best way to get the link to the slides communicated?
I will share those to everybody who
Okay.
registered.
Okay.
So if you didn't register, just go back and do it now, and I'll have your email address. On that question of resources, just specifically for different types of color blindness, do you have recommended websites or tools to put your figures in those different types?
Yeah, so if you're an R user, sorry, wait, what's the question to simulate?
Yes, exactly.
Yeah, so if you're an R user, there's the color space package. So it's the color space package, and it actually has this interactive app. It has a lot of stuff, but so here, like you basically the way it works is you can upload an image, and then it upload, like it's an app that runs locally on your computer if you run it directly from R, and then you give it an image, and then it creates these simulations. There's also a web page. It's called, it's not maybe so easy to remember, hclwizard.org. And it's a little slow, but it has this deficiency emulator where you can just upload an image, and then it will create this simulation. So that's basically that's what I do. But these days it's pretty. There's actually many different services, and like maybe like also Photoshop or so has that built in. I don't know, I don't use Photoshop, but I wouldn't be surprised if they did. So you can probably also just Google color vision deficiency simulation, and you'll find something other than this R package. But for people who use R, it may be the easiest to just like get familiar with the color space R package.
Any final questions from the audience? Yeah? No? All right, looks like we have answered all our questions. So I will just finish by thanking you, Dr. Wilke, for speaking to us today. I know I learned a lot, and we'll use some of these things immediately this week when I'm giving a talk.
Okay, very good.
Is there anything final you'd like to say before we close out? Maybe
Maybe just like thanking you for spending this hour with me and listen to me. And the other thing is, like, many of these topics, like in particular telling a story and so on, these are complex concepts that you will not necessarily pick up immediately, right? So just work at it, like over the next years or so, right? Like maybe difficult next week in a talk to fully apply all these concepts, but just keep them in mind, like read more about this, just start thinking about what is my storyline, what is the challenge, what is the resolution, and over time you will get better at it. Okay.
Thank you so much. Thank you, everybody. Let's give Dr. Wilke a round of applause. Thank you to everybody who joined us online. Have a great afternoon, everybody.
Okay, bye.